Okay, so we're using Pythagorean theorem for these first four, rather. Remember that Pythagorean formula can only be used in right triangles. It doesn't work in triangles that don't have at least that don't have one right angle. So you just make the legs, A and B, set those in. C always has to be the hypotenuse. And you want to solve for the C since the formula has C squared, you just square root both sides of the equation. And notice how I'm not doing intermediate calculations. You don't have to, you can just enter it into your calculator just as it is. And they want you to round the answer to the nearest tenth, so you get about 44.8 units. And there are no centimeters or inches on this. If there were, we would include those, but they're not in the problem, so we're not going to include them. Number two is the exact same thing. Again, you just plug those numbers into Pythagorean formula, and so you don't need to worry about the intermediate values. You can just calculate it outright, just like we did in number one. For number three, um, here we're still plugging them in, but notice how we're given the C, we're given the hypotenuse. So when we substitute that into the formula, instead of just being able to square root both sides right away, we got to move the 4.0 to the right side of the equation. Then we square root both sides, and here we have a subtraction sign instead of a plus sign between the values. You get zero point 0.9 as a result. Now, I've said I've been kind of flying through, not bothering with the intermediate calculations. Let me show you what happens if I do those intermediate calculations. You may be doing it like what you see on the right side of the screen, but it's a waste of time. It's not necessary unless you have, a situation where you're not allowed to use a calculator. There's really no point in doing those intermediate calculations. For number four, it's sort of similar to number two. We're given the hypotenuse instead of given two legs. We're given one leg and one hypotenuse. So you want to isolate the variable. So move whatever constants there are to the other side. And then once you have just that variable squared, you square root both sides of the equation. For number five, we're just confirming to see if this can be lengths that we can use to construct the right triangle. What that means is, do these three numbers work in the Pythagorean formula? Always put your biggest number into the C, because whatever the biggest number is, if it is a hypotenuse, you have to have the biggest number to be the candidate for the hypotenuse. These check out. So since both sides of the equations are equal to each other, it's going to check out. Now, you can also use test logic for this. Here, I'm asking the calculator, is 4 equal to 3? And it says no. And 4 is equal to 4, it says yes. You don't have to use this, but it's just a neat feature it has. Notice how if I put the, if I try to check my answer in the calculator and I properly square the 25, it'll output a yes. But that's just a neat feature that really you're probably never going to use. For number six, again, we're just checking to see if this works for the Pythagorean theorem. And so I'm just really testing both sides, either using the standard way or the test logic way. Now, for number seven, when we go to test it, I get a false value. And that's because if I try to test the second part, I don't get the same thing as for the first part. You don't need to know this, but notice how the 289, which is what we thought would be the hypotenuse, is less than the 320. What that ends up being is it forces it to be an acute triangle. If the right side were bigger, then it would be an acute triangle, but that's not something. For number eight, we're just simplifying radical expressions. The square root of 3 is already simplified. You can't reduce that anymore, but square root of 12 you can reduce into 2 square root of 3. So by prime factoring, that's a perfect square. It's a factor of that. Either way, you combine the coefficients, you get 3 square root of 3 as your answer. For number nine, the quickest way to do this is recognize that this is divisible by 100. 100 is a perfect square. And if you take the square root of 100, you get 10. So it's 10 times square root of 3. If that's too fast for you, if you'd rather just do it by prime factoring, you can just keep pulling out prime numbers. And then just like we did when we first learned this, anytime there's twin sets of those prime numbers, you kind of cancel them out and write them outside the radical. Here I'm using the little wedding cake method, and I'm pulling out the twins. So there's a 2, 2, 5, 5, 3. Since there's two 2's in the radical, that makes 1, 2 outside the radical. Same with the 5's, and you still get 10 square root of 3. So that's the other way of doing it. We could also do it using a factor tree, but it's the exact same way as my second method, and you get the same prime factorization. You still get 10 square root of 3. So there's three ways of doing that problem. For number 10, all we're doing, we have like terms. This is like, think of this as 4 potatoes minus 1 potato gives you 3 potatoes. and the square root of 10 can't be reduced. For number 11, we have 18 is something that can be reduced. So I'm going to prime factor to reduce that. The same thing with 12. 12 is it's a pretty big number and it can be reduced. And I usually don't like to, if I have a negative, we don't like to leave it on the in the denominator, and it's in the numerator here, and that's fine. But we reduce both of those radicals, however you choose to do it, either recognizing perfect squares or prime factoring. And if something can cancel out, you do. Notice how the 3 inside the radical on the bottom will not reduce with the 3 outside the radical. So don't think that you can cancel those out. But what we want to do, we don't want to leave a radical in the denominator. So we rationalize it by multiplying the bottom and the top by those radicals, or you could also multiply them by their conjugates. And then we get on the bottom, we no longer get a radical, and then we reduce that where we can, so we end up getting negative square root of 6 over 2 as your final answer. And you could write that either with a negative included in the numerator, or you could put the negative out front. Either way is fine. For number 12, we're going to work at least 3 examples of these. Whenever you have a radical expression on the bottom, you got to multiply by the conjugate to rationalize it. So the conjugate, remember, is the same. It's the same binomial expression, but except there being a plus, there's a minus, or vice versa. So I'm working it out the long way and showing you that, if you simplify the bottom expression, you end up getting 3 minus 16 because the middle term cancels out here. You get negative 13. So you could write this as your final answer. I don't like to leave negatives in the denominator in my final answer. It just looks kind of weird. So it looks a little better if you kind of either write the negative way out front, or if you write the negative distributed across your numerator. So this second way is a slightly better way of writing it, but we could distribute the negative, get negative square root of 3 minus negative 4. But you could also just not lead with a negative. You could put 4 minus square root of 3 and then put all of that over the denominator. For number 13, same thing. Multiply by the conjugate. So the conjugate here is the same expression, except instead of there being minus between the two terms, there's a plus. Now, I mistakenly write square root of 24 here because I saw that square root of 6 and I saw the 4. And I thought, oh, let me multiply those. But it's the square root only applies to the 6. So it's actually 4 square root of 6, or 4 times square root of 6. So you write 4 square root of 6 right here. And we can divide everything by 2. So you can factor a 2 out. So it's actually 2 square root of 6 plus 3 all over 5. So just make sure you write it in reduced form if you can. You can do that reducing your head, or you can factor it out. Number 14 is the same thing. We got to multiply by the conjugate on both the top and the bottom to get the radicals at the bottom, because remember, we want to rationalize the denominator. So you distribute the square root of 2 on the top, and then on the bottom, actually I had the wrong conjugate here, so this is supposed to be a minus because in between the 2 is a plus. So then the bottom, you just FOIL or do whatever you call it, distributive property. If I simplify this, I get 2 squared minus 3 squared, which is 2 minus 9, which 2 minus 9 is actually negative 7. So I should actually write negative 7 here. Arithmetic, very hard. And then you just simplify like terms where possible, distribute and all that. Square root of 2 times square root of 2 is just 2, and then minus 3 square root of 2. Now, we don't like a negative on the bottom. I wouldn't mark this wrong if you left it this way, but it just looks weird to have negatives in the denominator. So we could instead distribute that negative across the top. And since we're leading with a negative, you could also write the positive one first, minus the negative one. For number 15, we can multiply radicals together, and so we're kind of practicing doing that. We could also just put both of these radicands, remember, the things inside of radicals, under one little radical sign. I can factor out the 10, and so I see that actually inside of this I have 2 5s, so a 5 makes it out of the radical to join up with that 3. Later we're going to be multiplying those. And there's 2x cubes, so 1x cubed can make it out. Another thing you can do is just see that as x to the 6th power and just recognize that the square root of x to the 6 is x cubed. But either way, you simplify. This is your simplified answer. For number 16, We're solving radical equations. Now for this, you just want to get the x by itself. So first move the 4, then square both sides to get that expression out of the radical, then divide by 2, and so you get y equals 4.5. You could also write 4.5. You could leave it as 9 over 2 if you prefer improper fractions. And we're going to check that in a bit, but first we'll look at 17. Again, get the k by itself. Don't be tempted to write 6 here, because you might think, oh, square root of 36 is 6, but this isn't square root of 36. It's square root of what gives you 36. So the answer to this is to get the k by itself, you have to square both sides, so we end up getting 1296. But the way to check both answers, I just check it in my calculator, since you're going to be calculating this anyway. And one neat little trick is I can actually take this 1296. So if we check this second one, I can store that into the variable x, and then just write the expression as I see it. I could also store it into the variable k if you prefer. But if I do square root of the variable minus 8 and I get the equation coming out to be true, then I know that I got the right answer. You could also just manually enter in 1296 and place at the k. For number 16, again, I can store that 4.5 into the variable and just enter the expression exactly as you see it. And if it comes out to the correct thing on the right side of the equation, I know I did it right. Or you can just manually put in that number. For number 18, the goal is to solve for the variable. So just do whatever you got to do to get stuff away from that variable. I multiply by 3 on both sides. I square both sides. And then I subtract 2 on both sides. And I divide by 3 on both sides. So I get m equals 7/3. Or you can say m is equal to 2.3 repeating if you put in your calculator, or 2 1/3. What form you put the answer in doesn't matter. And you should always check your answer. And on an equation, you can always check your answers by just plugging in what you think the answer is into the variable and just making sure that the equation comes out to be a true statement. So you just check the answer, it comes out right, then you can be confident that your answer is right. For number 19, we're going to start by squaring both sides, and then you just write what's inside those expressions. And we just get all the x's on one side, leave the constants on the other side, and we get 4 equals x. Again, you can just check your answer by plugging 4 into those equations, and you end up getting on both sides square root of 12, either way you do it. So you don't even have to go as far as actually square rooting it, but if you do it in your calculator, you can see that 4 is the correct answer. The reason we check the answer is because sometimes you get an answer that's not truly an answer. So for our number 20, start by squaring both sides. You end up with a quadratic equation. And in quadratic equations, there are 2 solutions to those. You got to have that in standard form to solve quadratic equations. So let's move everything on one side of the equation. And here I wrote mistakenly the plus 2 there. It should actually be a minus 2, which I'm going to correct that. So that makes this become x squared plus x minus 2 equals 0. And there's 2 ways to solve that once you get a quadratic equation. You can either solve it by factoring. So when we say solve by factoring, I mean, kind of like breaking it down into 2 binomials that multiply together. And you can use your rules to figure that out. And you get the solutions are x equals 1 and x equals negative 2. And if you don't want to solve it by factoring, you can use the quadratic formula, which is the negative b plus or minus square root of b squared minus 4ac all over 2a. But instead of using that, we wrote a program, remember, to use the quadratic formula. And you just enter in your coefficients, which are 1, 1, and negative 2. And it gives us those same answers, 1 and negative 2. Now, it seems this has 2 solutions, but if we actually check these answers, let's check the first solution, 1. So plug 1 in place of x into the left side of the equation, and what it should output is another 1. Okay, well, that one works, so that one checks out, so x equals 1 solution. But if I plug in negative 2, if I do 2 minus negative 2, it should output negative 2, but it doesn't. So that means that the negative 2 is actually not a solution. So that means that the only solution here is x equals the positive 1. So we call this an extraneous solution, where we think it was a solution, but when you check it, it actually isn't. And that sometimes happens when you're solving square root equations. Some of them are not actual solutions. For number 21, we want to square both sides to get rid of the radical. And when we do that, we again arrive at a situation where we're going to be dealing with quadratic equations. So you want this to be written in standard form, and I can do that by, instead of moving everything to the right side, moving it to the left. And I normally don't like dealing with a negative coefficient, but if you use quadratic formula, it handles that negative coefficient just fine. And again, we get two solutions, but what's going to end up happening here again is that one of those solutions will be extraneous. The negative 6 checks out, but if you plug in the, what was it, a positive 1, what we expect on the right side is negative a. Well, negative a would be negative 1, but it outputs positive 1. So that means that the positive 1 solution isn't an actual solution, it's extraneous. And so the only solution here would be x equals negative 6. You could also solve this by factoring if you want, but I don't like factoring with a negative coefficient leading out. So you just divide or multiply both sides of the equation by negative 1, and that takes care of that. You solve by factoring, but you end up having to check the answers the same either way. That's why I just prefer using quadratic formula. For number 22, the most important thing you have to know here, we did a gizmo talking about this, is how that plus 2 changes the regular square root equation. So y equals square root of x is kind of the sideways shaped parabola, or at least the top half of it. And that plus 2 moves it 2 units to the left. And that's what you have to know. So you need to know how those numbers shift the function. For number 23, it's very similar, but instead of plus a number inside the radical, it's minus a number. So this actually shifts it. That should be 3 units. It shifts it 3 units to the right. So if you look where the minus 3 is, I move 3 units to the right, like so. And that's how it translates or shifts or modifies the square root function. For number 24, the plus 5, notice how it's outside the radical? That means it's not going to move it left or right, it's going to move it up or down. So again, the standard square root function is graphed here. And if we shift that thing 5 units up, that's what the graph will look like. If it was a minus 5, it would be shifted 5 units down. But just some more examples of comboing those two. Kind of questions you need to answer is, how do these numbers affect it? Either it moves it left, or it moves it down, or it moves it right, or it moves it up. You need to know how each number, depending on where it's placed in the function, modifies the graph. So these are all going to be vertical shifts or horizontal shifts. The one difference is, we talked about in class, if you have a number out in front, just so we can review that this 3 right here is not a vertical shift. It's a vertical stretch. It makes the function taller, or if you put a negative, it flips it upside down. But that's not something you're going to be asked about on the test. You need to know about the vertical and horizontal shifts. Number 25, this is another one just like the first 4. We're just using Pythagorean theorem. So you can quickly calculate this, run it into the formula, and you get 29. Number 26, same thing. This is the one very similar to numbers 3 and 4. You're not given the hypotenuse, so before you go trying to solve it in Pythagorean theorem, you got to get everything to one side, and you still calculate that. Number 27, we're doing trig here. So we first want to label everything we're given. We're given a right triangle, and then we're given the hypotenuse, and we're given an angle. It doesn't matter where you put the angle. I could have put the angle 50 degrees. I could have put that on that bottom right corner, but just because I'd happen to draw my triangle this way, I'd put it in the big angle. It just makes more sense to scale, but how you draw your triangle doesn't really matter. The opposite side is the thing we're looking for, which is the side opposite of the 50-degree angle. When we use opposite and hypotenuse, we know that we're using sine. So the sine of the angle is equal to the ratio of the opposite over the hypotenuse. So the angle in this case being 50 degrees, we don't have the opposite. So we'll just put a variable there. You can put any variable. I'll use x. The hypotenuse is 10 centimeters. And so to solve for x, we need to get rid of the 10 by multiplying by it on both sides. And at this point, this is the exact answer, 10 sine of 50, but I need to use my calculator. Make sure it's in degree mode. And so if I just enter that in, you get if you round to the nearest tenth, about 7.7 centimeters. So just knowing which trig function to use by labeling your sides helps. For 28, this is just an exercise. We talked about this in class, where the sine of one of the acute angles is the same as the cosine of the other acute angle. And I drew an example here. I'm just using the 3, 4, 5 triangle. It's the most basic right triangle. The sine of angle A is 4 over 5. Well, the cosine of angle C is also 4 over 5. Something that's interesting is that your tangents of the different angles are reciprocal to each other. Don't worry about 29 or 30 so much. Even though like 30, it's the converse isn't always true. You can have other numbers that give you hypotenuse of 5. But number 31, we've done that several times. You should know that to get rid of the radical on the bottom, you multiply by the conjugate. But let's look at 32. All they ask is the diagonal a rational number? Well, rational means that you're not going to have any square roots in it, or at least not any square roots that can't be reduced to an integer. So if we calculate this using Pythagorean's theorem, what we end up getting is square root of 9 plus 9, which is square root of 18. That reduces to 9 square root of 2, and since square root of 2 is not a perfect square and it can't be reduced any further, this is going to be irrational.